Welcome to Operations Management, Week 3, Lecture 3. Today we tackle the question every manager eventually faces. You have studied a process, you have measured it, and you have found the constraint. So what do you actually do about it? Here is our roadmap. First, we will look at the 3 levers of process improvement. Second, we will separate work that adds value from work that does not. Third, we will look at yield and scrap, and how quality losses quietly eat your capacity. Then we will work 2 full examples together, one on yield, one on choosing between improvement options. We will finish with a 6-step decision framework you can apply to any process. Let's get started. Before we dig in, let's be clear about where we are headed. By the end of this lecture, you should be able to do 5 things. Apply the 3 levers of process improvement. Tell the difference between value-added and non-value-added activity. Explain what yield and scrap rates are and why they matter to flow. Calculate how yield loss changes the quantity you need to start with, and weigh improvement options using a cost and benefit lens. Notice the key question at the bottom of the screen. You have found the bottleneck. Now what? Everything today is an answer to that one question. This is where analysis turns into action. Let's ground all of this in something you have actually experienced. Think about the last time you waited too long for something. A table at a restaurant, a package that never showed up, a support call that left you on hold. In almost every case, the cause is the same. A process had a constraint and nobody dealt with it. Look closely at the photograph. On the left, one cook is buried. Tickets are hanging in a row above the pass, and pans are stacked up in front of him. Now look to the right. Those cooks are standing still, arms crossed, waiting. Nothing is wrong with them. They simply cannot work faster than the station feeding them. That imbalance is costing the manager money every single minute. So what are the options? Our text gives us 3 levers. That kitchen shows us the problem. This slide gives us the toolkit. Look at the 3 levers on the graphic. The first is staffing level. You add people at the constraint step to raise its capacity. It is the most direct move, and it is also the one that costs money. The second lever is offloading. You move tasks away from the constraint step and give them to steps that have room to spare. This is often the best value because you're using people you already employ. The third lever is balancing. You spread the work more evenly across all the steps, so no single step is far more loaded than the rest. That cuts idle time and waiting across the whole process. Now read the rule at the bottom of the screen, because it governs all 3. Always apply these levers at the constraint first. Improving any other step does not raise your flow rate. It just makes a fast step faster. Before you spend money on any of those 3 levers, ask a cheaper question first. Is this work even necessary? That is what this slide is about. A value-added activity transforms the unit in a way the customer will actually pay for. Cooking the meal, assembling the product, diagnosing the patient, writing the code. A non-value-added activity burns time and resources, but adds nothing the customer values. Waiting in a queue, moving materials from one place to another, re-inspecting work that was already inspected. In Lean, this second category has a name, Muda, and we will return to it in a later module. Now look at the number in the middle of the slide, because it should stop you. In most service processes, only 5 to 15% of total flow time is value added. The rest is waiting, moving, and rework. That is the opportunity. Removing waste is usually faster and cheaper than buying capacity. Look for waste before you hire. So far, we have assumed every unit that enters a step comes out the other side. Real processes are not that kind. Yield rate is the share of units that successfully complete a step. Scrap rate is simply 1 minus the yield, the share that fails or has to be reworked. Here is why this matters. If a step yields less than 100%, you must start with more units to finish with the same number. and the scrapped units are not free. They consumed capacity on the way to being thrown away, which makes the constraint worse. The formula is on screen. Required input equals desired output divided by yield rate. Look at the three examples. A bakery at 90% yield bakes 111 croissants to deliver 100. An assembly line at 95% needs 105 boards to ship 100. A hiring process where 80% of offers are accepted needs 125 offers to fill 100 jobs. And here is the part students miss. In a multi-step process, these losses multiply. Overall yield is step 1 yield times step 2 times step 3 and so on. Let's put that formula to work. On the left is the problem. Brooklyn Print Company makes boxes in 3 steps: cutting, printing, and folding, with yields of 97, 92, and 95%. Follow the middle column with me. Question A asks for the overall yield. We multiply the 3 yields together, and we get 0.8479, about 85%. Question B asks how many boxes must enter cutting to deliver 500 finished boxes. Divide 500 by 0.848, and you get 590. Notice we round up, because you cannot make a fraction of a box. Now read the insight on the right. Out of every 100 boxes that enter, only about 85 reach the customer. 15 are lost along the way. And which step do we fix first? Printing at 92% is the weakest link. Same logic as the bottleneck. Always attack the weakest link first. Yield tells you where quality is leaking. This next example asks you to spend money wisely. Flatbush Urgent Care checks patients in through 3 steps. Registration handles 20 per hour, triage handles 14, room assignment handles 18. Triage is the constraint, so the process runs at 14 patients per hour. The target is 18. Now walk the middle column with me. Option A adds a triage nurse for $35 an hour. Triage climbs to 19, so room assignment becomes the new constraint at 18. That hits the target. Option B offloads 2 tasks from triage to registration at no cost and lifts triage to 17. Better, but short of the target. Option C adds a registration clerk for $22 an hour. Registration was never the constraint, so flow rate stays at 14. That is money spent for nothing. The recommendation is on the right. Start with option B, because it is free and gets most of the way. Then add option A if you still need the last patient per hour. Never invest in a step that is not the constraint. We have covered a lot of separate pieces. This slide ties them into one repeatable routine. Look at the 6 numbered cards on screen and follow them in order. 1. Draw the process flow diagram, so every step, cue, and handoff is visible. 2. Measure the 3 metrics, inventory, flow rate, and flow time, and apply Little's law. 3. Find the bottleneck, the step with the lowest capacity because it sets the flow rate for everything. 4. Eliminate non-value added steps first. Look for waste before you spend on resources. 5. Apply the 3 levers at the bottleneck: staffing, offloading, and balancing. And 6. Account for yield losses. Work out the input you need and improve the lowest yield step first. Notice the order matters. The cheap diagnostic work comes before the expensive fixes. Follow these 6 steps and improvement stops being guesswork. Let's bring it home with 5 things worth remembering. First, the 3 levers, staffing, offloading, and balancing, only raise output when you apply them at the bottleneck. Second, eliminate non-value added work before you add resources. Waste is usually the biggest and cheapest opportunity. Third, yield losses multiply across steps. 3 steps at 95% each give you an overall yield of only about 86%. Fourth, remember the formula. Required input equals desired output divided by overall yield rate. And fifth, look ahead. In our next lecture, we add the formal analysis tools, process charts, service blueprinting, and process technology, which make this framework sharper in practice. Take a moment to review the two worked examples before then. Thanks for watching, and I will see you next time.